So I'm Angie I'm a postdoc at CalTech. Today I'm going to tell you a little bit about machine learning for the real world, provable robust extrapolation. So machine learning has been very successful in many business applications, but in some of the real world tasks, we're still not getting there. For example, if we want to do fine-grained species classification, our accuracy is very limited for certain classes. And for example, if we want to do zone control, we still do not know how to handle some of the weird dynamics. And usually how we do machine learning, so we collect some data and shuffle them and try to make training and test look the same. And the reason we do that is because the theory tells us if you have large data, and there will be some good generalization bound just due to concentration inequalities. However, the real world is not like that. Your test samples is usually not very represented in your training data. For example, if you want to do species classification, you may have data collected from America, but the test data is coming from Africa. Or if you want to do drone landing or drone flying, you have some training model that's in the clean and nice lab environment, but then when you deploy it in the wild, you get some weird wind condition you've never seen before. Or if you have structures maybe for hovering, that's trained very well, but then the drone is actually doing landing or flying close to some weird surfaces you've never seen before. So ignoring this shift can be potentially very risky. In this example, if you have blue training samples and you train a model that's a linear, and then for the test sample, you just extrapolate. By extrapolation, we mean you just apply or generalize your data there that's for the test data you've never seen before, then the potential risk can be very large. And imagine how about in a safety critical region where you can risk humans' life and every mistake you make is like really, really important. So a sequential learning problem can be seen as a domain shift problem in every iteration of exploration. For example, if you want to put your Mars rover in a new environment, it only sees the state space in its old data and does not know the whole world. And then every step exploration, you try to enlarge your state space and try to shift a little bit from your original data. So that's already domain shift. And the things can be even trickier if you have a region in your state space that you can never touch, which is labeled as unsafe. So our goal here is to enable machine learning algorithms to be aware of domain shift and extrapolate accordingly, such that they can be integrated to the real-world system to satisfy safety-critical requirements. And how do we get there? We propose to use some classic tools from the virtual estimation. We do novel derivations under domain shift and also are able to incorporate deep neural networks. And then we're working on the applications and integrations to the real-world system. I'll skip the technical details here and welcome to my poster to listen to all the details. I just want to show this example of landing. In this case, we want to teach the drone to land as fast as possible, but also safely. And in the first iteration, it has very conservative landing trajectories. And you can see it cannot even land. It will hover there because of the ground effect. And after 5 epochs, it can land faster and also stay away from the unsafe region. So as an outlook, predictive performance is not the whole world. In reality, we care about safety, we care about fairness, and all these other issues. And in my opinion, to achieve those goals, robust extrapolation under domain shift is really the key problems we need to solve. And I'm happy to talk with any of you in the poster session. Thank you.
Hi, welcome everyone. So yeah, I'm a postdoc at NYU, and I'm going to speak about why low-resource languages are a challenge for NLP in general and at the moment specifically. So recently there has been a lot of progress in NLP due to deep learning and due to really big models being used for tasks and also in general for pre-training. So what people are doing is they use huge amounts of text that we have available mostly on the web, so like Wikipedia, for example, and then they take models that have a lot of parameters and train them. So popular examples are BERT, which is some sort of language model used for pre-training, which has been trained on about 16 gigabytes of text. And then, like the same year, GPT-2 came out, similarly also a language model, but has been trained on 40 gigabytes of text. And then, because the first one, BERT, got really, really famous, people continued with like all stuff like Albert, or this one, Roberta, which is basically BERT, but using cleaner data and more data. So here we have 160 gigabytes of text. So yeah, this has worked really surprisingly well, and in many cases has surpassed human performance on some tasks. Yeah, so, yeah, this has been possible because we have these huge corpora for English, right? So, for example, for English, Wikipedia has 49 million pages, which is a little bit less than the 16 gigabytes, because BERT has been trained on Wikipedia plus some other smaller corpus. But then if we look at other languages, like Chinese, for example, Spanish, German, which are usually considered kind of high-resource languages in NLP, for those, we have only 5 million pages in Wikipedia. Then Norwegian has only 1 million pages, and the last one you can see is supposed to be Afrikaans, which has like 200,000 pages. So this means that we can train these models and they work well if we look at English because we have this data. But we cannot train the models the same way we do this for English, for example, for Afrikaans. And of course, there are like several thousands of languages that don't have Wikipedia at all, so we cannot like train this model at all. And this is only like the case for like pre-training, where it's relatively easy to get data, like because we use unlabeled text. And this is like even worse for like task-specific data, where we have much less or fewer resources available for English, but much more so for the other languages. So yeah, basically, so my research is like focused on how can we make NLP work for those languages that are not English, that don't have these resources, and there are a lot of areas that enter there. Like one would be to develop models that are very like efficient and can learn from very small data sets. One is to develop methods for transfer learning. One would be to collect data sets, even though usually it doesn't sound very cool, but it's necessary. And here I'm going to talk about the second area, about how we can develop methods to like use some sort of transfer learning. And one option that has been used is multitask training. So the idea here is you have one task which has a lot of data available, one task that doesn't have a lot of data available. And by saying task, this could be any sort of combination of language and task as well, right? So for example, question answering in English could be one task, and question answering in French could be another task. And the general idea is you take this task with a lot of data and the task with like little data and kind of train one model on both of those tasks at the same time. And you usually do this by like having some combined loss function for like both tasks. And you can use different options for parameter sharing when doing this. Like for instance, you could share just like the lowest layer, that is the representation of words, like word embeddings. You could share the entire model and have different output layers. In some cases, you can share all parameters of the model and use, for example, some sort of task or language embedding. Like there has been a very famous system from Google that was like training translation on a bunch of languages at the same time. And then there's another method, which is called self-training. And here we have another idea. Here the idea is we want to use unlabeled data for a specific task, even though we don't have the labels for training. And what you do here is you take a model, well, like an architecture, you train it on the data you have. And then you assume that your model is kind of already good at the task. You use the unlabeled data as input. You get the labels from the model and use this as silver like standard annotation. And what you usually do there is you filter by some heuristic. So you say like, okay, we assume this model is kind of certain about those examples, so we add them to the training set, and we discard the others for now. And then what you can do is you retrain the model on the extended data set, and then you can repeat, right? So you can label again and retrain. And yeah, the work I wanted to talk about was that we combined these two. So we combined multitask training and self-training. And yeah, how we did this was, so we have an auxiliary task with a lot of data, a target task, and then we train first a model on the auxiliary task data and use it to label the test data from the main task with the idea in mind that the heuristic here, like why is the model certain, is that the auxiliary task is for some reason easier than the main task. Like either because the task is just like a lower level, easier task, or because we have more data. And then we use multitask training to train the model on the main task data, the labeled auxiliary task training data with the main task labels and the auxiliary task training data, and use this model to get the final predictions. Yeah, and this is like the set of tasks we tried this on. These are the results, but yeah, we can talk about this at the poster. And yeah, I wanted to thank my collaborators, Johannes Bierwa and Isabel Augenstein, and of course, all of you for listening.
So this work is called visual deprojection, and the goal of this is to recover imaged data from projected observations. And this is in collaboration with several others at MIT. So first of all, what is a projection in our work? In our work, we consider a projection as something formed from an n-dimensional signal like this, superimposed in some direction. So we see here that this image on the right basically aggregates all information in a particular dimension. So where do projections actually arise in practice? Well, they actually arise in a lot of different imaging scenarios. Here are just three. On the left is an example of long exposure photography, where something moving over time gets collapsed in time into a still image. This, by the way, is an image of star trails over the night. X-ray images can be considered as projections of 3D anatomy in space. And an emerging, exciting field is non-line-of-sight imaging, where hidden scenes are often collapsed to give you some low-dimensional observation. In a lot of these applications, it would be really useful if we can go from projections back to the higher dimensional signal. So for example, with X-rays, if we can recover CTs from X-rays, it could be very, very useful in practice. So the goal of this work is, can we recover a distribution of plausible high-dimensional signals given the low-dimensional projection? And we want a distribution because this task is highly ill-posed, and so we don't just want one solution. And in our work, we apply this to different cases. I'll touch on the first at the end of this 5 minutes, which is recovering images of faces from their spatial projections. But we also worked in different other scenarios, such as recovering videos from temporal and spatial projections. I think it's worth spending a small amount of time thinking about this problem in the frequency domain, just because this is what's often done in tomography. So on the left is some kind of two-dimensional signal, and on the right is its Fourier spectrum. Actually, this probably isn't its Fourier spectrum, I just kind of made it up. But if we take the two-dimensional signal and project it in some angle theta, we get this projection P of theta. The interesting thing is this projection slice theorem tells us that the Fourier transform of that is equal to a slice of the original Fourier spectrum. And so you can think of our problem as saying, can we recover the full Fourier spectrum given just one slice of that spectrum? And so you can think that this is extremely an ill-posed problem, and we need priors to do this. So at a high level, we rely on data to actually do the deprojection. So we have paired training data of projections in faces, in this case, or the faces are the signals, and we use this to train some learning model that can go at test time, take a projection, and spit out possible signals that could have generated. And so our task now is how do we create this learning model? And at a really high level, we first have a probabilistic model relating projections and signals. Inference on this model leads to an objective function with parametric functions that we implement with neural networks, like Justin said, because of course. And we train this network on data of a particular domain so that at test time we can deproject in that domain. So now I just want to leave you with a teaser result. We're going to show results on flicker faces, which is a data set of 70,000 diverse face images. We train a model, this is training set images, we train a model on these data to deproject from spatial projections. So these are test images of faces, the true images, and these are the horizontal projections of these faces. So test time, we give only these projections to our method, and the method spits out these samples of faces. So these, again, the model only sees the projection, and yet it's able to reconstruct images of these faces that are remarkably close to the actual faces, indicating that these projections have way more structure and content than we would believe. One small failure case is on the bottom where you see the lips are kind of smeared with the background. But overall, it's pretty good. So some takeaways from this project are we introduced this learning-based deprojection method. Results show a surprising degree of hidden information that we can recover. And we believe this has important implications in many different imaging fields and also tells us something about image and video data that we didn't know before. Thank you very much.